Okay. Um, what I want to do today is show you some interesting thing. I was talking to my kid. He's 14, is in middle school, and I was trying to teach him a little, not to be afraid of math, because what happens is all these academic guys, they make make math so difficult, so hard, that it's the kids get so scared. And the reason they make all this math so hard is with symbols and all proofs. And when math is in fact like so easy and so down to earth, it's a tool to solve problems. And I look at math as an engineer, as a tool, as a hammer, or cement to build things. When you look at that way, things like artificial intelligence and neural networks and Fourier transforms and SVDs, all this stuff is so simple. And I want to show how I explained him how simple it is, how straightforward to understand. So I want to make relationship between, let me select the brush, one is good. Okay, I want to make a relationship between Fourier transform and love. Yeah, I'll get there. But so let's just look at how. Let's start with love, because Fourier transform, you probably know what it is. But let's look at things like Match.com. How these guys started. So what they did actually is very, or for that matter, Netflix, right? When you select a movie and you like a movie, like an action movie, Schwarzenegger or Stallone, and they know that you are gonna like movies like that, action movies. You're gonna probably like Bruce Willis, and if you like drama, they just know that you like drama. They will offer. But how do they do that? It's very simple. It's the same way that they match people. Um, let's say that you have one guy, and this guy goes to Match.com and starts answering this questionnaire. So he says, he's asked the questions, do you like cats? And you have to answer something 0 to 10, give a score 0 to 10, and I say, all right, not much, give a 5. Do you like dogs? I'll give that's a 7 for me. Do you like math? Yeah, I mean 8. Tracking. I say, yeah, well, not so much. Fishing, sports, and that goes. Let's give you this 7 again. Sports 10, and you go like this. Well, and you get a woman. That's pretty skirt. And she's asked the same questions. So now you have two sets of parameters, right? One for each one. Let's come up with some numbers for her. This is just random. 8, 2, 5, 9, 1, 2. All right, so these are the numbers for her. And how do you come up with a match to know if they are a match for each other? What you want is really from these two numbers have some kind of operation that is going to act on them and output something that's again 0 to 10. Well, let's say these guys are, let's look at this, these guys are 6. So from 0 to 10 they are 6. They are a match, but not a very good match. And the way they do this is it can be very simple. I don't know exactly what the algorithm is, but the way you can do this in a very simplistic way is you transform each. Let me go back. What you do is you just multiply one number by the other. So 5 times 8, 40. 7 times 2, 14. 40. 4 times 9. Geez, I'm getting old. 36. 7. 20. Right? And then you sum all this. 40, 14, 40. 4, 10, 17. Carry 1. 8, 10. 13, 15. 157. But what does 157 mean? I want something between 8 to 10. Well, the problem with this 157 is that I multiply numbers that are between 0 to 10. So if these guys were to give 0 to 10 for each one, you need to find a way that the results are bounded somehow. And the way that you do is if you sum up all these numbers, you're going to see that this is 7. So this 12, 20, 24, 31, 41. And this 8 to the 10, 19, 24, 25, 27. And if you look at the maximum that it could be, it would be like if they give both 10s to everything, that would be like 10 times 10, 100, 6 times. So this would be 600, right? And the sums, they would be 60 and 60. So you see the maximum would be 600 and the maximum here would be 60. So you see that there is a relationship between this number and this maximums here. And ends up is the easiest way to do this, to make this work, is just normalize it in such a way that both sums are 1. If both sums are 1, what you have, so in this case you divide each of these by 41, right? And this you divide by 27. If you do this, you see that the multiplication is going to be 40 divided by 41 times 27. And when you sum this up, this is going to be 157 divided by 41 times 27, which is all right, so 157, 41, 27 multiplied, divided, 0.1418. Okay. So what's the deal here? I want to make this normalized. So if I gave the maximum, that would be 600 divided by 60 times 60. Right? So obviously I need to do something such that this is normalized. Notice that if I just do a square root, I'm cheating here. But this is going to be 600 divided by 60. Right? This is going to be 10. So they would have a 10. So if we do this, let's see if it works. 41 times 27, 157. Let's go back to the calculator. So this is 157, 41, 27. I'm gonna multiply these guys, and then I take the square root and then divide. 4.7. So here we go. We have a match now of 4.7 between the two, not a 6, but a 4.7. That's more or less what we want. We want a single score, then we can relate this man to this lady, or I mean whatever, man to man. We don't know these days. But this they have these two people have a 4.7 score between them. That's a match? No, that's below 5. I mean, it's then you keep changing the lady, or keep changing the guy. You match all the people against the database, and you have the best scores. With the best scores, you just display back to the guy in the website as a match, and hopefully you make some money in the process of connecting them. I'm not sure if this actually works, but if people that match well, if it leads to happy relationships, but that's mathematically that's the idea behind all these sites. Netflix uses the same thing. So you watch movies. Movies have characteristics, drama, and so Pandora does exactly the same. So this is a simple math used to that. But the question now is, what does this have to do with Fourier transform? That was my first question. What Fourier transform has to do with this? All right, so let's look at a moment what we can do. If you have two numbers or two, so in this case you have a sequence, two sequences of numbers that you normalized and then you multiplied, and you obtained a number. Oh, and by the way, if you want to do the square root, you have to divide by the square root of this sum. Alright, just going back there. So this is going to be the square root. Then you have a normalized number. Now that's the process you need to do. Divide by the square root of the sum. Okay, so now you have this very interesting part. Because if you have a Fourier transform, what's Fourier transform? Well, given a sequence of numbers representing, say, audio, so you have a 0, 0.5, 1, 0.5, 0, minus 0.5, minus 1, minus 0.5, 0. Of course, I mean this number, this is supposed to be what I'm trying to build is a wave. So if this is an audio and these numbers represent volume levels, So this should be something like this. Goes up, goes down, and to 0. So this is I mean, if this is like 1 second, then this is a 1 hertz sine wave. What to do is, so we have the man. Okay, now we have to find the pair to this man that does a perfect match at 1 hertz. And what's the best solution? Let's see, if we put everything 1, right? What we're gonna have is so this is gonna be pretty much like the original series: 0, 0.5, 1, 0.5, 0, minus 0.5. And by the way, if this is a sine wave, this number should be square root of 2, which is about square root of 2 divided by 2. It's about 0.71. But leave it 0.5 just so I can make these calculations better. Alright, so this is the sum. I multiplied this number by this number and put it here. So because everything is 1, then I just repeat the original series. So this, and then I sum it all to have a match. So it's 0.5. This is 1, 2. This is minus 1. Well, minus 2, 2 minus 2. The sum of all this is 0. What it's saying is that this sine wave with a constant, the match between them is 0. Which makes sense. I mean, a sine wave has nothing to do with a constant. So what kind of wave will maximize the match between the two? Well, the match between the two will be the maximum number of the sum is obviously this is negative. We have to get rid of these negative numbers here and have more positive numbers. So the only way to do that is that I multiply by something negative in here. So if I get 1, 1, 1, 1, and then minus 1, minus 1, minus 1, minus 1, that would be nice. So if we do this, we have 0, 0.5, 1, 0.5, 0, and then plus, plus, plus. And the sum is going to be 2. Right? Which is good. But the maximum that you get is actually the same wave. 0.51, 0.5, 0, minus 0.5, minus 1, minus 0.5, 0. If you do this sum, you're going to see that this number, of course, we have the normalization factor here. It's going to be square root of the sum of all these two. This number is going to be bigger. So the wave that maximizes the match between our original one and our synthetic wave is itself. I mean, because the is the sine, because the original one is a sine wave. And that works for any wave. The match is going to be itself. So what we're doing with Fourier transform is matching an original wave to a candidate wave. Of course, it's not only that. I mean, Fourier transform has more, has other characteristics, like it's normalized, and it has spectral properties and so on. But when you go back to wavelets, wavelets work exactly this way. Wavelets can be way more complicated than Fourier transforms if you go the mathematical way. If you go this way, in the matching, in the filling of the numbers, wavelets are so simple that any programmer without with high school math can start compressing videos, compressing images, and that's pretty much how I explain to my kid what spectral analysis is, and how wavelets are. What you're doing, you are just matching, doing a love match between the wave that you sampled from the physical space and a synthetic wave that you created manually in by a computer. So that's, and then you have a score of a match. Then in the end, what you got is, hopefully I can get some space here. Okay. Then in the end, what you have is frequency, right? And here is the match between the two, and then you have a big match on the frequency, let's say 1 hertz, on the frequency that matches the original wave. So that's what Fourier has to do with love. Thank you.